So this is a course on algorithm design and analysis. We meet on Mondays and Tuesdays from 2 to 3:20. That's my name and that's my email ID. You're welcome to send me an email, for any clarifications, fixing up a time to meet, or if you have any questions on assignments or any such thing. So for IIT Jodhpur folks, unfortunately I can't see you guys, but hopefully this thing will be fixed soon that I'll be able to see you. Pratibha is the TA. This is also a sort of a second course for people at IIT Jodhpur, and for all of you, you've all done some courses on design and algorithms. So I'm going to assume a lot of things. And so we will actually talk more about different kinds of paradigms in this course, rather than going through sorting and searching and basic data structures and graph algorithms. These are some of the things we assume, but we might get to them if there is a need, and we'll quickly revise, and you should be able to read up and pick up things even if you have not understood it very well before in your previous course. Okay, and I'll just give you a list of tentative topics we will cover. We're going to look at for example, you would have seen worst case complexity analysis of algorithms. Some of you might have even seen average case analysis, but we will look at it in some depth. This notion of amortized complexity, it's more relevant in the context of data structures. So in this topic, we will look at different kinds of heaps, splay trees, and so on. So we look at dynamic programming as a paradigm. Greedy. Again, you all would have seen some of it, but maybe if I know that many of you have seen this thing, we will go quickly on some of those topics. Yes, divide and conquer again. We'll look at some examples. We'll look at randomization, and we'll spend quite some time on lower bounds. So how do we show that this is the best you can do for certain problems, right? So in terms of adversary arguments, and also eventually get to NP completeness. So it is possible that many of these topics are sort of a repeat for you if you have actually done these things, but hopefully we will do it at more depth, and there will be a lot of opportunities for problem solving. So this is a more problem solving course. There will be enough for you to do in problems. Okay. So today I'm just going to give you a very basic motivation. This is some first lecture I do. It's very simple. Why we care about algorithms, right? In fact, many of you undergrads would know that big companies, their interview questions are all about data structures and algorithms. We'll see why, right? And I'm just going to walk you through a very simple example. And this is sort of a introductory lecture I give to wide spectrum of audience. But since you guys know enough, I'll do it faster for you. So let's start with a simple problem, A and B. Okay, large is the keyword of, let's say, some numbers. When I say large, each one is in the order of some 10 power 10 size. Okay, so think of it like maybe an array of Aadhaar numbers or something. Right? It's like a billion numbers are there sitting in two different versions of them. And the question we want to address: find all common entries in A and B. Okay, maybe there is nothing common between them. Maybe there is some. I just want to find all those values which are in both A and B. Okay, and N for us is very large. So what would be a very simple brute force algorithm? Okay, so can you say it in terms of a for loop or something? So let's say both have cardinality n, which is this large, right? So it's a very simple algorithm which simply says for I going from 1 to n, if A of I is equal to B of J, then
so we have to add it to these two.
yes, so let's create a new array, some C array. C of K is A of I, right? So when K is incremented, and K is maybe initialized somewhere to 0 or something. This is it, right? Very simple algorithm. And this, imagine these are like two large arrays of other numbers. Maybe two different government departments have this big arrays and they want to find out, are there any duplicates? Can you collect all of them? Okay, now how much time does this algorithm take? N squared, right? Because you know how many times this AI equal to BJ step is executed. For every I, you run through every n times. So for there are n i's, so you're going to do n times n. So there will be n squared steps this algorithm will proceed. Right? That's simple algorithm. N for us is like 10 power 10. So this is like 10 power 10 square is what? 10 power 100. 10 power 20 steps. Good. So now, your modern laptop or current computer, how many instructions do you think they can perform in 1 second? Anybody knows? I mean, if you have done some informatics Olympiad programming or something like programming contests, you will see that they give examples such a way that your program should run in 1 second or something like that. And the expectation is that 10 power. So 10 power 9 instructions is what you can do in 1 second. So let me approximate it and say, suppose your computer performs 10 power 10 instructions. In 1 second. Then to perform my 10 power 20 steps, how many seconds?
10.
Not 2 seconds? No? You won't believe. 99 out of 100 times when I ask this question, people have said 2 seconds. Okay. So, to perform my 10 power 20 steps, our computer will take 10 power 10 seconds. And 10 power 10 seconds, you know? Very large. Years. How many days? How many years? You can do some Google search quickly, and it's about 316 years or so. Okay. It's a very simple problem, important problem. We have a very simple algorithm, n square algorithm, and for the reason, I mean, you don't see it in, I'm sure many of you have programmed. You don't see things taking 300 years. I mean, you're not going to wait and see that long anyway. But so why is this? Because you never try it on a data of a billion size, right? You're going to try on examples which are of size 100, 20, 1,000, 10,000 maybe. Okay. So suppose if my n is 10 power 5, then how many seconds will it take? Can you just 1 second? Because n square is 10 power 10. 10 power 10 instructions you can do it in 1 second. So that's a big difference. So 10,000 is typically kind of sizes you would have tried. For that it will actually take 1 second. But as you see that as n increases, in particular if it's close to like 10 power 10, this is just, impossible to do it in your lifetime, in our lifetime. And typically, if people do program, companies do have such large data, and if you do an n square algorithm, it's going to keep on running, and you'll come up with some excuse, oh, my internet is slow, or it's infinite loop or something like that. No, it's not expected to stop in reasonable time. Okay. So let's think of a better algorithm. Can you think of a better algorithm? What should I do? Same problem, you have two large arrays A and B, each of size n integers each, and I want to find entries that are common to A and B. What can I do? You should be able to say this. Okay.
Sort the array B.
Sort the array B. Okay. So here is a suggestion. Sort B. Then, okay, using merge sort like algorithm is what he says. Okay, I'm just writing whatever you're saying. Okay. What advantage does that get you? Okay, he's even saying that you can sort in order of n log n. Okay, this is refreshing your memory of whatever you learned. There are lots of n log n sorting algorithms. What are some? Merge sort is one. Quick sort. Heap sort. You're not happy with quick sort. Why?
The average case for quick sort is n log n, but
Quick sort is not an n log n algorithm. Quick sort works on the average n log n, but quick sort is an n square algorithm. Okay, this is how I bring in things you are supposed to know, so that if you did not know, you should just go look up, make sure you understand it, right? So quick sort. Okay, what does average mean? Average over what?
average over all possible instances of size level.
There are lots of instances of
Not
size.
all possible ordering of size.
All possible orderings of input n. If you just do this deterministic simple quick sort, the average number of comparisons made by this algorithm is n log n, but in the worst case it could be n squared. Okay? But there is merge sort, there is heap sort, there are several other n log n sorting algorithms. You can sort B using that. Okay, now so what? How does that help you?
We can do a binary search on
So now for each element in A, do binary search in B. And then, if you find it, you will add it to your array C and increment and all that. But these are the two big steps which we hope will bring in that improvement we are looking for. Okay? So, lots of things, right? So, binary search. What is binary search? When can you do binary search? If your array is sorted and you have a query element you want to look for in the array, you can do binary search. How does it work? Compare with the middle. If it is smaller, go to this side. If it's bigger, go search this side. And one can argue, analyze. How much time does it take each binary search?
log n.
Log n time, right? This is very, very important. Make sure you know it. You know the proof of why it takes log n. So why does it take log n time? Is there a quick
Every
one?
step you are reducing it by n by 2.
So every time you reduce the list by a factor of 2, right? So how many times you have to take a number n, keep dividing by 2. how many times you have to divide by 2 so that it becomes less than 1? This is exactly the definition of log n. How many powers of 2 are sitting in n? Right? So that's exactly what's happening. So that's log n time. So now, for each element in A, to search for you check whether it is in B by doing a binary search. So let me even instead of saying big O, I'm going to just say n log n. Merge sort takes a little bit more than n log n, a little bit less, but let's stick to n log n. So for each element in A, I'm going to do binary search in B. So that's another n log n. Now, whenever you find this, you add it to your RAC and do all that. So now how much time does it take? No, overall, our algorithm takes 2 n log n. Typically, when I do this to a different kind of audience, I have to spend half an hour on binary search and tell why it takes log n. But since you all know it, we're going ahead with it. But if you did not know it, please go check the books and make sure you understand what binary search is and why it takes log n time. So now we have spent 2 n log n time, right? Let's do our calculations for our n, right? N is this big N, right? So this is 2 times 10 power 10 into log 10 power 10, right? Log is to the base 2. This is the number of steps made by this algorithm. So what is this? So it's log 10 power 10, 10 times log 2, log 10, and what is log 10? 3 point something, right? Why? Because, as I said, how many powers of 2 are in 10? 2 cubed is 8, 2 power 4 is 16, but it's between 3 and 4. So 2 into 10 power 10 into log 10, I'm even going to give it a 4. This is the number of steps made by the algorithm, right? This is the steps. So how many seconds?
8.
This is 80 seconds, right? Because we know that we can do 10 power 10 steps in 1 second. Quite dramatic. What was the n square algorithm taking? Some 300 something years. Whereas this simple thing that, why don't you sort and do binary search? In our mind, it's n square and n log n, and you think about, does it really matter in these days of powerful computers where computers can do huge number of things? It matters between 300 plus years and 80 seconds. Okay? So it's now we will see later in the course that this is between n square and n log n already, and we will see later on that you can't even do it in n cube time, n power 4 time. There are problems where you need to spend exponential amount of time and so on. So the game is quite different there, and you need to do something even more drastic to solve those problems feasibly. Okay, so this example should give you an idea that when n is large, in the order of 10 power 10, even n square is useless. Okay, for 10 power 5, 10 power 6, 10 power 7 maybe. And all we have done is, as computer scientists, you're supposed to know about sorting and searching, and that's all we have done. Okay, good. So this is a quick, introduction to why we care about algorithms, and that's what we're going to do in the whole course. Now let's revise something else you're supposed to know. So now I have an array, sorted array. You all told me that if I want to search for an element, you can do binary search, right? So Now I tell you, if X is not there, please go ahead and insert it into the array. Then how fast can you do? What do you do and how fast can you do? Right? I want to now support both these operations, both search and insert.
Order of n.
If you want to, okay, what do you do?
Even if we search using binary search,
Yeah.
we don't find the element, then we'll again use the binary search algorithm to find the exact position in which we have to insert it.
Why do you have to again use it? Okay.
Yeah, we can find the
Ah.
position at which we can. Yeah.
Right. So binary search gives you the position where you need to insert. So for example, this was 17, and then the next element was 27, and if you are trying to insert 23, when you do binary search, you know that 23 is not there. It will also tell you that 23 is there. This is where it should be. So now what you can do is just insert 23 into that position, but you have to move everybody to the right. Of course, I could just go and insert 23 at the last position.
No, but then the array won't be sorted.
And so,
We have to sort it again.
you have to answer these queries. So you are welcome to do whatever you want. The array won't be sorted, so you can't search fast. So you have to pay a price either in search. Right? If you keep it unsorted, you have to pay a price in terms of search. If you keep it sorted, insertion takes linear time because you may have to move elements. Now somebody might say, okay, insertion, you have to move elements, so why not use a sorted linked list? Right? Because now when you know where the element has to be inserted, you just create a new box and insert it and then you done. Yes?
Middle element not
Yes. No. So he says there is a problem. What's the problem?
So in that case, the searching becomes difficult.
Searching becomes difficult. How do you search? How do you
Right.
how do you do binary search? What is the first step in binary search?
Directly taking the middle element.
I have to compare X with the middle element. How do you find the middle element if you have organized your data in a linked list? What is the important difference between linked list and an array? That in an array you can index it to a location directly. In a linked list, the access is only through the beginning of the list. I only know the beginning of the list. And then for every element, who is next? So you have to traverse your list like that, starting from the beginning. You can't just do binary search so easily. Right? You can do binary, you can do, but just do linear search. Right? This is data structures 101. Just want to remind you, refresh you, if you have not thought about this, right? Big difference between linked list and array is that yes, there is a dynamic memory and all that, but more important thing is in an array you can index. You can just go, I want to go to 177th position and get that element. You can directly get it in constant time. In a linked list, the access is only from the beginning. So that doesn't work. So if I want to do insert and search in logarithmic time, what can I do? Sorted array, sorted linked list doesn't work.
Binary search.
Okay, do what is called a binary search. You all studied this without thinking why we needed this. So that takes us to okay, what is a binary search tree? So it's a tree. What's a tree? Well, there is a root and every node has a left child, right child, or both, one of them or neither, right? So my binary search tree will look like this. and I have values sitting on the nodes. What is the property of the value sitting on the nodes?
Left child will be less.
Yeah, left child will be less and right child will be greater. So I might have it's not just left child is less, the entire left subtree is less. Okay? There's some subtle differences, so it's important. So that's a binary search tree where it's a tree, every node has a value with the following property that anything on the left subtree is less than or equal to anything on the node, which is less than or equal to anything to the right. Now I can search into a binary search tree, I can also insert into a binary search tree, right? How do I search? Exactly the way I will do binary search, compare it with the root. If the element I am looking for is smaller, go to the left, otherwise go to the right. If it's equal, you are done. And then continue the same procedure again. And if the element is not there, let's say for example 66, which I want to insert, then the search will take me to this nil pointer and go and insert 66 and be done. No movement, nothing, no pushing around like what we were doing in an array. So that's the beauty of binary search. Okay. But how much time does it take to insert and search?
No.
Why log n?
No. Height of the tree.
It's proportional to the height of the tree.
Okay.
Okay, so the time it takes is proportional to the height of the tree. But what happens to the height of the tree? How do we, So the height of the tree, for example, if this is all I'm doing, the way I just described the algorithm, I'm going to search, and if they go to the empty location and insert it. Suppose next I'm trying to insert, let's say 14. My search will take me here and I'll insert 14 here. Then I might insert 12, I might insert it here, 11. What happens? There's no control on the height of this tree. Right? It can become as bad as a linked list. So what do we do? So that takes us to this notion of height balanced by the research tree. Right? Again, you have seen them all. I'm not going to do any of them, but hopefully I'm trying to motivate you why you need them. Right? Because if I want to support queries, insert and search and delete in logarithmic amount of time, then a sorted array or a sorted linked list or a simple binary search tree is not good enough. So you need height balanced binary search trees. There are a number of them you would have seen, AVL trees, red-black trees, there's some 2-3 trees, B trees, and so on. Which again I assume you all have seen some version of it. So if you have not seen this and if you want me to do it, please send me an email, and if sufficient number of people have not seen it, we will do it here. How do they work typically, right? So let's pick something like a red-black tree. I don't want to go into the definition, but I just want to give you an idea of how these height balanced trees work. What is our goal? Our goal is to keep the height logarithmic at all times under these operations. Because when I am inserting, the tree can change. When I am searching, the tree won't change. Search, if I make sure the height is logarithmic, search will be logarithmic time. But when I am doing insertions or deletions, it can destroy the tree. I have to do some rebalancing, make sure the height remains logarithmic. And that's how these data structures do. What do? They maintain some sort of a local property, right? So what Okay, maybe let's do AVL. So, in a perfectly balanced binary search tree, what will you have? You will have exactly, it look like this, right? I mean, I need to add this because the number of nodes is not power of 2 minus 1, maybe more, so I need to fill up this level, and maybe this is like this. But if I start insisting on such a tight constraint that I want the tree to be balanced, then every time and every insertion may cause a huge amount of changes I need to do. There's always in the area of data structures, you always have a trade-off between, if you keep a lot of structure, it helps you to do your query faster. But when you are inserting or deleting, you need to do a lot of work to maintain the structure. So you need to do some relaxation, right? So AVL trees basically tell you that for every node, you look at the height of the left subtree and height of the right subtree. Ideally, I would like them to be the same, but AVL tree relaxes and says, okay, I keep it plus or minus 1, the difference. Okay, so is this an AVL tree? Let's see. Okay. So we'll go node by node. So if you look at this node, the height to the left is 1. Okay, you just go from that node to nil pointer. The height to the right is 0. So the difference is 1. That's fine. If you go to this node, on the left is 0, on the right is 2. The difference is 2, so it's not an AVL tree, right? So AVL tree tells you that you just sort of maintain it with the height difference between the left and the right at most 1. Okay. Typically, each of these balanced binary search trees will have a certain constraint like this on the tree. Right? It may be constraints on every node. Red-black tree will say that every node is colored red and black, and a red node cannot have a red child, plus some more constraints. Okay, so there will be some sort of constraints. And what you want to show based on these constraints is that first is that height of this tree on n nodes is what? What do I want? So there's going to be a trial for a lot of things. This is first property we want because this is what is going to help us support the search operation in logarithmic. And for AVL tree, one can, typically this is shown using some sort of a recurrence relation. So assume you have a height h. Look at the maximum number of nodes it can have. So if the height is h, or look at the minimum number of nodes it has. Okay. If this root has height h, one has height h minus 1 and the other right side will have height h minus 2. Because if I am talking about the minimum number of nodes. So now write a recurrence relation. The total number of nodes in this minimum number of nodes will be th minus 1 plus th minus 2 plus 1. Okay, and this recurrence sounds like Fibonacci recurrence, right? Because th minus 1 plus th minus 2, and the solution to this is 1.618 power h. So the number of nodes with height h is at least 1.618 power h. Okay, so if n is the number of nodes in the tree, then because this is the minimum number of nodes any AVL tree with height h. Okay, I ran a quick proof using Fibonacci. So from here you will get h is at most log n to the base of h. That's what we wanted to show. Right? And this is typically the first step you want to do for any balanced binary search tree, that after you create this local constraints, based on the constraints we will argue first the height of the tree is at most logarithmic. That immediately implies that the search algorithm will take logarithmic time. Now to do insert, what you need to do is that we will do a normal insert as you would first search for that node and find an empty place and you will insert it like this. But then it might violate the local constraints, AVL tree constraints. So there will be some case analysis. The algorithms will do some rotations on the nodes to maintain the AVL tree and bring back to make sure all the constraints are satisfied. So typically each insertion algorithm will have a bunch of case analysis depending on where you are trying to insert the node, and it will give you a way to fix the constraints violated in the process, and all that will argue that can be done in your logarithmic time. Okay, and this is just the template for any balanced binary search tree. Moment some constraint is given, first thing you argue is that the height is logarithmic, and then you come up with some methods to insert and delete so that. So I'm not going to do these things, but it's important for you to know that these balanced binary search trees exist, in which you can do insertion, deletions, search, all in logarithmic time. They come very handy when we talk about complicated algorithms. Okay, good. So that's a quick revision of sorting, searching, why algorithms are important, and data structures. Now I want to get on to this notion of amortized analysis. Okay, so now when we get to the notion of, so we've all seen worst case. Good, I can see the people there. Very good. So we have all seen worst case analysis of algorithms, data structures. Now I want to just introduce this notion of amortized complexity. So where do we use data structures? Well, data structures can itself be your problem, because you ask Google for a query, you want it to come back and give you the answer very fast. So you want an efficient data structure which can process your query and come back with the answer very fast. So worst case is important there, right? Because you want the answer quickly. So that's one area where it's used, and worst case is important. But other place where we will use data structures is when we are implementing a complex algorithm. We will think of a nice data structure, we will load it and repeatedly ask some queries and operations on that, and we will run our algorithm. Okay. So in those applications, the worst case is not all that important. I care about, so let's say I'm doing my spanning tree algorithm, okay, minimum spanning tree, Dijkstra shortest path. If you've seen these algorithms, how will you, an efficient implementation of these algorithms will use heaps, priority queue, and you'll use heap So you set up a heap and you are doing some queries on that heap data structure. For the efficient running time of the algorithm, it doesn't matter if one query takes more time, if my overall sequence of queries take less time, right? So amortized complexity is all about not analyzing the complexity of one operation, but for a long sequence of operations. We do care about worst case, but worst case not for one operation, but worst case for a sequence of operations. Okay? So I want the total running time for a sequence of some A operations to take a certain amount of time, right? And I want to measure this quantity. Of course, so let's say a sequence of some P operations. We know that this is clearly at most P times the worst case for any operation. We know that because if you know my data structure will take log n in the worst case, and if I am performing P such operations, in the worst case it's going to take P log n time. But is it the correct estimate? We don't know. Why do we ask this question? Because maybe the worst case doesn't happen all the time in your sequence, right? So maybe one worst case operation will make subsequent operations much better. Then maybe you have a tighter estimate, right? So here's my favorite example which I always use. Okay. So I want to understand what is your monthly expenses, right? So I ask, what is the maximum you spend on any single day? And I will multiply by 30. So you say I spend 3,000 rupees for my mess bill on 2nd of the month. So I'd say, okay, your monthly expenses is at most 30 times 3, 90,000. Which is absurd, right? Because the reason you spend 3,000 is to amortize your cost. Instead of paying every day, you paid it once, right? So that made your rent for subsequent months, subsequent days 0. Because you paid it once, subsequent days rent is 0, right? So as long as I put this less than or equal to, I am not wrong. Because I say it's at most 90,000, yes, it's correct, but it is not a tight estimate. Okay? So one thing we want to do is to come up with ways to measure the time for not just one operation, but a sequence of operations. And why it's difficult is because you want to capture the relation between these operations. How one expensive operation changes the data structure so that the later operations can become cheaper. Right? We need to somehow capture this and makes it all the more difficult. So there are two things to it. One, we want take the existing data structures and somehow we want to measure the cost for a sequence of operation. Other is if my goal is only the sequence of operations and not for one, I may want to come up with different data structures to meet this purpose. Rather than worst case, I will be happy to spend more time sometimes, but it just sort of amortizes better. Okay? So the difficulty is actually how do we analyze this cost for a sequence of operations? How do we capture one operation does something to the data structure, and how do we capture that? Right? That's what makes this a little subtle and difficult. Okay, so we'll do some very simple examples. This is all from Corman's book anyway. So let's look at this following example where I have a k-bit counter and I want to do some increment operation. Okay. So if I want to increment a k-bit, so let's call this some P0, P1, P2, K minus 1. So this is a k-bit counter. Each one is a 0 or 1. And I want to increment this. What would be an algorithm to increment this? Increment. So think of this as an array of size k.
D0, D1, etc. are zeros and ones.
Everything is a 0 or 1. Yeah.
So if dk minus 1 is 0, then if you increment, you just have to change it to 1.
Change it to 1. Okay.
If not, then you have to change that to 0, and all the previous ones, like all the ones that preceded, like.
So just here is the algorithm, right? I start from the right and look for the first 0. And flip all the ones to 0 till that point and change the 0 to 1. Right? So let's say I start with some t equal to q minus 1 while dt is 1. Flip dt and t equal to t minus 1. And then when you come out of the loop, my bt was 0, I'm going to change bt to 1. So that's an algorithm. Right? So start from the right, keep flipping all the trailing ones to 0. Okay? That's what I meant by flip. So this is same bt is 0. Until when do I get out of the loop? When bt is 0. At that point, I'll come and change it to 1. So assume that my first bit is always 0. So now, how much time does this take in the worst case? And what is time? Let's say how many times I'm flipping this bit. The k bit counter. So if it is like 0, 1, 1, 1, 1, 1, 1, 1, I'm done. I would have changed all the ones to 0 and changed the 0 to 1. So how many flips I would have done? I would have done k flips. Right? So in the worst case, k flips. But suppose I start from 0, 0, 0, 0, 0, 0 and do some n increments. This is a sequence of operations I'm doing, right? And I want to understand the total time for this n increments. Again, it's at most trivially from here n into k, but I want to know, can I say something better?
Yes, because I'm not sure, but the bit B0 is flipped once, and the bit B1 is flipped twice, and
So let's start from the bottom at the end.
That is flipped n number of times.
Okay, so her observation is dk minus 1 is flipped all the time, so n times. So my n is clear, I would say is less than or equal to 2 power k. So I don't come all the way up to 1, 1, 1. So bk minus 1 is flipped n times, okay?
Dk minus 2 is flipped n by 2 times.
Is flipped n by 2 times. You all see this? Because the moment you flip the last thing from 1 to 0, the subsequent increment will just change the 0 to 1 and stop. It won't even go to the previous bit. Okay? Now you can guess what's going to happen, right? dk minus 3 is flipped n by 4 times, right? Because see, it's important I said starting from 0, 0, 0, 0, 0, right? Keep that in mind. So you will have 0, 0, 1, 0, 1, 0, 0, 1, 1, and then it's flipped. So this 0 is flipped to 1, and after next 4 flips, this is not going to be touched again. So it's going to be flipped n by 4 times, and so on and so forth. So what is the total time? So total time, if you n plus n by 2 plus n by 4 plus n by 2 power k or something. But heck, even if I go all the way up to infinity, what is the sum? It's a geometric series. 2n. It's a geometric series. This is at most 2n. 8 is not kn. We get a better value. Right? So what we say, what is amortized cost? It's actually average cost per operation for a sequence of operations, right? So I would say the amortized cost is like 2. I haven't formally defined amortized cost, but I'll do it next time. Regardless of k, okay? K may be 200 bits. I'm trying to do this increment, and the amortized cost is almost 2. So now here is a simple example. Okay, there are several things. I said starting from 0, 0, 0. Does it matter? If I start from something else? Not much. It doesn't matter actually. It matters a little bit. We'll see why. But this is a very simple example where we could somehow globally look at this, and I can have a good snapshot of all the n increments, and in an aggregate level tell you that, oh, this bit is incremented this many times, and I can do this analysis, which is often not possible when we get to something like splay trees or something like that, where we will do this amortized analysis. Okay. So now, Slater and Tarjan, who introduced this, came up with another nice idea of capturing this amortized analysis. Is what is called using what is called a potential. So the same thing, I'm going to analyze it slightly differently. What we want to, so basically the way I want to think about it is, I want to give some budget to each operation, each increment operation. And I want to see how much budget I should give. Okay. So now if the operation has more than what it requires, it will put the balance in the data structure. Okay. If it needs more than what I am giving it, it will take something from the data structure. So now I want to be able to give enough budget so that any operation which is expensive, which needs more, has enough in the data structure to get, borrow from, and it will meet its needs. Okay. Now this 2 gives an idea of how much I want to give it to each operation. So I'm going to give each operation a budget of 2. And that budget turns out to be the amortized complexity. We'll argue that. Okay. So, okay, I'll come to the potential later. So each increment comes with, I don't know, budget, comes with something. Cost. Okay, supply, comes with the supply. If it needs less, place the balance in the data structure. Because we are working in the data structure, right? In our case, the k-bit counter is the data structure. and if it needs more, borrow from the data. Or not borrow, because I'm going to give it back. Take from. So this is sort of a setup. So the question is, how much do I have to give each operation so that if it needs more, it has enough in the data structure. And I claim that I'm going to give each increment operation a supply of 2 units, whatever, right? Which is to pay for all the flips it's going to do, because the essential cost of the increment operation is the number of flips, bit flips it's doing. So I'm going to give it cost of 2. Okay? So the first increment starts. How much does it need? Because it's starting with 0, 0, 0. It needs only 1. So it has an excess of 1, which is it's going to put it in the data structure. The next operation, again I'm going to give it to 2, but it's going to take 2 units of time because I'm going to flip this. But there is already 1 sitting in there. That's okay. I'm going to keep the 1 there and use this 2 to pay for it. Okay, so now data structure has some 1 unit left. This is how we keep track of it. The next operation is going to perform 3 flips, right? Oh, just 1 flip, sorry. It's doing only 1 flip, so it is having an extra 1. So now the data structure has 2 units. The next one is going to do 3 flips. So I'm doing 2 and we still have data structure as something extra 1. Okay, so this is how the whole thing will go. And I want to argue that at any point of time, if you supply each increment 2 units, that's enough. There is enough in the data structure, because remember, some increment may be something like this. And it's going to change all of this to this. It's doing a lot of flips, but even then, I want to argue somehow that there is enough in the data structure for this excess guy to take care of. Okay? So now, how would you argue this? So I'm going to call this potential of the data structure is the number of credits it has. Okay. So what I want to say is that if my operation takes less time, I'm going to add more, the potential will increase. And if it takes more time, I'm going to take from the data structure, the potential will decrease. Okay. So the actual cost supply, which is what I'm going to call it amortized cost, less so this is the potential after the operation, this is before the operation. Right? So if the actual cost is more than what I am supplied, that means I'm going to take minus. Let's see why. So if the actual cost is more, then the potential will decrease because I'm going to take from the data. So the potential after will be smaller than the potential before. So this will be a negative number, and with a minus it will plus. So that supply plus whatever I'm getting will be the actual cost. If the supply is less, I'm going to throw into the data structure. So after will increase. So this will be a positive thing. So the actual cost will be less than what I'm supplying. So typically, this is what I want to compute, right? In general scenario, I want to compute the amortized cost. So the amortized cost is equal to the actual cost plus the potential difference. Now, what is this potential? I mean, how do I compute it? Okay, I said intuitively the potential is the number of credits the data structure has. And the big challenge for us is to come up with this potential, which captures how much data, the credit is there in the data structure. Okay. So, any guesses for this increment thing? So, what is an expensive operation? Something like this. Lot of ones are flipped. Okay. So in that case, potential will drop, right? So what has dropped here, from here to here, in the data structure? Number of ones. So number of ones is a natural choice here for the credit, the potential in the data structure. Now if you see, a simple one-liner, suppose I say, so another way to do it, think about is that suppose everyone has a credit of 1 unit. Okay. Number of ones is the potential, which is the number of credit. This is my intuition of how much is in the data structure. It's going to be number of ones because this is what is useful for an expensive operation. If I have everyone as a credit, then whenever 1 is flipped to 0, I don't have to use my supply. There is a credit sitting there. I will use that credit, right? So all the 1 0 flipped are paid for by whatever is in the data structure. I use my supply to change 0 to 1. How many 0 1 flip happens in any increment? Exactly 1. So I use 1 credit to pay for the 0 1 flip plus I created a 1 and I have to maintain the invariant that every 1 has a charge. So I keep 1 more unit on that. So 2 is enough. Okay, that's all. Right? So if I just say this is going to be the number of ones, then whenever, so one can now easily, if I just define, so by magic I just define this. Okay, now we got all the intuition for this problem to say this, but later on we will see that there will be some magic that will happen. But once I define it, let's analyze the amortized cost, right? Suppose the increment operation performs some L flips. Okay, it varies from 1 to k is what we saw. Suppose the actual cost, it performs L flips. Then what happens to the potential difference? You will see that out of the L flip, L minus 1 are 1 0 flips. So the number of ones has dropped by L minus 1. Not quite, because I'm also going to create an extra 1. So it's L minus 2. So it's the potential difference will be minus or L minus 2 because it's a drop. And this is equal to, right? Because if I've made L flips, this right. Increment made L flips implies L minus 1 1 0 flip and L 0 1 flip. Right? So the potential drop which is 5d after minus 4 is minus of L minus 2 because that's a drop. So the amortized cost is the actual cost less the potential difference. Right? So we had an aggregate way of analyzing the whole thing, which gave us an intuition of the amortized cost is 2. But from there we can come up with this notion of potential and this. So later on we will see some data structure example where I want to compute the amortized cost. I'll come up with some magic potential function on the data structure and then argue and analyze how much my algorithm changes the potential. If the actual cost is something, and plug it into the formula and you'll get the amortized cost. Okay? So amortized cost, remember, is just the notion, it's the average cost over a sequence of insertions. Okay? When you say average, there is no distribution, no probability, nothing happens. It's just that take a sequence of operations, look at the worst case, divide by the number of operations. And that is the average cost per increment. And that for our increment operation is 2. So now when I have this potential, so which means if we do P increments, total cost is 2 times P, right? That's what we saw. So now let's come back to this potential thing. Suppose I don't start with 0, 0, 0, 0. Then what will be the total cost? See, remember, the potential in the data structure is the amount of credit. Another way to think about it, this is some people may think of amount of over counting we have done. Because if I say an increment takes at most 2 units, the first increment actually takes only 1 unit because it changes 0 to 1 or 1 to 0, 0 to 1. So I have over counted it. That's the extra 1. I'm going to store it later on. I will do some undercounting to balance this. Right? So you can think of it as a credit, think of it as the amount of over credit counting we have done, that eventually things will balance out to 2. So now if I don't start with 0, 0, 0, 0, 0, and I need to put credit on the ones, right? Because later on some 1 0 flip, I'm not going to supply it. Actually, I'm going to use the credit. So you can add this total cost to the number of ones in the beginning. Think of it as an extra thing cost. So total, right? Let me just say this, and you can think about it. Total cost, if we don't start with okay. All zeros is basically 2 times P plus number of ones in the initial counter. Oh, you can also arrive at this from here. Okay, I'll mention that next time. So, yeah, so suppose I sum over the amortized cost, right? This is for an increment. Suppose I do it for all possible, because there is an after and before this particular operation. So I do a sequence of these increments and I add this amortized cost over all these increments. Okay? This, from this formula, the summation actual cost plus what happens? So imagine this is my initial configuration of the data structure. First increment brings it to D1, D2, and I have this DP after doing this P operation. Right? So the amortized cost for this operation is actual cost plus this potential difference, D1 minus D0. The amortized cost of this is 5 actual cost plus 5 2 minus 5 D1. There will be some telescopic cancellation that will happen. So this will be P of DP minus, right? Now my interest is here, because I just care about the total cost for the sequence of operation, the actual cost. So this is what? This is summation over amortized cost, which I analyzed it for this is actually 2 times the number of operations. And this thing will come in here, phi of d naught minus phi of dp. Okay. So phi of d naught is the number of ones in the initial configuration. So total actual cost is equal to total amortized cost less by d naught minus. And we always choose the potential so that it is greater than or equal to 0 all the time. So I'm going to now ignore this. Suppose, this total so yeah, if I did not start with all zeros, then phi of d naught, the potential on the initial configuration is the number of ones. So this we already checked is 2 times p plus number of ones. So to summarize, we will see more examples. This is really a toy example. We'll gradually build into more complex examples. That sometimes worst case is not necessarily a good measure of analyzing, especially on data structure queries where you are performing a sequence of operations. And so why is this happening? For example, if it was like this and one increment changed it to this, it produced a lot of zeros, which is good because subsequent operations are going to be fast. Because to get to this much more cost, you have to do a lot of increments. So you can sort of amortize the cost of this expensive increment for these, these guys who are going to do the increment. That's just sort of distributing the cost in some sense, right? Some of them are going to spend 1 unit, some of them are going to 2 units, and suddenly there is a 10 unit thing. The 10 unit I'm going to distribute it to those who spent only 1, and say that amortize it's actually unit of 2. Okay, and so worst case may not necessarily be a useful measure. So amortized analysis is useful, and often it's not so easy to capture how an expensive operation gives rise to a cheap operation. And a potential argument is one way to do it. And challenge is to come up with a good correct potential function, which may not always be easy. Yeah, so we will see more examples next time. And okay, let's stop here. So basically you had a good revision of sorting, searching kind of things, data structures, balanced binary search trees. Please go revise them. We may keep encountering them. And we will actually look at good amortized structures for something which you already seen, like heaps and balanced binary search trees in the next few lectures. Okay, stop.